All right, with that, we are ready for our next speaker. And for this next talk, I want to bring on Auryn, who is the founder of Nosa Guild, to talk about why modularity matters and how you can take advantage of all the upcoming things in the world of modular blockchains and just architecture. So with that, please welcome Auryn on stage and hope you enjoy how to think about modularity.
All righty, testing. All right, hey guys. So in 2012, I was riding the bench for an MBL team just down the road from here, the Wollongong Hawks. I was the fourth string big behind a handful of veterans. We're down 15 points in the third quarter against the league-leading Perth Wildcats. They're on this 5-game winning streak, super hot, and our starting center, Larry Davidson, goes down with an ankle injury. Our coach, Gordy McLeod, looks down the end of the bench and calls my name. And so what turned out to be one of the better games of my short NBL career, I managed to slow down Perth's star center just enough for us to fight back and come away with this really huge upset win. So hey guys, I'm Auryn. I've been contributing to the Ethereum ecosystem for around a decade for a variety of different roles in a variety of different organizations. Most recently, I'm the co-founder of Nosa Guild. We build a whole bunch of modular tooling for the Ethereum ecosystem. And now I bring up the kind of basketball backstory here just to give a bit of context on how and why I value modularity so highly when it comes to system design. In basketball and most team sports, having a variety of different players available to plug in into various positions in response to the current situation, the opposition, time and score, injuries, where you're at in the season, all this good stuff. It's really critical to creating resilient teams that can consistently perform well. Teams that rely too heavily on one or two specific players or strategies become as fragile as those specific players or strategies. And the best teams are adaptable. They can adapt to the current situation by modifying their composition or their strategies. In short, by being modular. The basketball teams are these dynamic systems. And these same principles apply to just about any dynamic system, from a sports team to a blockchain and everything in between. Next slide. So what is modularity? Simply put, modularity is this design principle of implementing systems as combinations of separate components, each serving this distinct function in a greater system. These components or modules can be independently developed, replaced, modified, without necessarily impacting the rest of the system. We see lots of gestures towards modularity all around us, the most classic example being the humble Lego brick. But modularity is exemplified in everything from Minecraft to IKEA furniture to music synthesizers. And in technology, modularity allows for more robust, more adaptable systems. Partly why Unix is such a stable and secure operating system is because of its insistence on these modular design principles, allowing users to add, remove, and create arbitrary chains of components based on their specific needs. Similarly, WordPress extends functionality through modular plugins and themes that all operate on the same kind of core site. And the software development platform Docker puts applications into modular containers, making them portable and easy to manage across different compute environments. So to help think through this a little bit more, it's useful to compare modular systems to more monolithic systems, where all of the components are tightly integrated. You can think of these monolithic systems as single, indivisible units where changing one aspect often means significant changes to the entire system. This design might simplify the initial development and deployment, but it can quickly become cumbersome as systems grow and evolve in response to changing user needs and environmental conditions. For example, updating a single feature in a monolithic system can often require redeploying the entire system, which really complicates maintenance and introduces huge amounts of risk. This is akin, using the basketball analogy here, akin to a one-on-one basketball team. So in a one-on-one scenario, the team's ability to respond to any given situation or adversity is entirely dependent on this one player. No personnel adjustments based on time and score on opposition, no capacity to deal with injuries or foul trouble, ultimately a fragile system, a system as fragile as that one player. Modular designs address this kind of fragility by separating stages of a process into discrete components, often with layers of redundancy. But modular designs are not all made equal. An important and really often overlooked distinction should be made between closed and open modularity. So by closed modularity, I mean systems where module production is either permissioned or modules are inseparable from some given core component. Could I take this module and plug it into a different core component? The answer is no. There's a good chance that this is a closed modular system that exists in service of some kind of monopoly. A classic example is two-sided marketplaces, like Amazon, the Apple App Store, Airbnb. They offer this form of modularity where sellers, consumers, developers can freely participate on either side of the marketplace by offering or consuming products and services, but their core components are not modular. An app developed for iOS cannot easily be run on non-Apple devices, for example, and you can't easily port your Airbnb listing and reputation into another booking platform. The explicit justification for this Closer? Sorry, there we go. Okay, so the explicit justification for this kind of closed modularity is generally around ensuring a degree of reliability and uniform performance across all modules, guaranteeing a baseline user experience. Apple's ecosystem is, again, a really classic example of this, where hardware and software are really tightly controlled to ensure this seamless integration and user experience. But this comes at a really significant cost to both users and developers. Ecosystems of closed modularity, more often than not, are used in service of cornering some market, and retaining users, and ultimately extracting value from them. This is achieved by making modular components that are overly dependent on one core component or vendor that cannot easily be replaced. We can see this distinction with Lego and IKEA that I mentioned earlier, both of which are really classic examples of modular systems, but are ultimately closed due to their patents and complex licensing structures, which inhibit third-party participation and innovation and limit user choice and control. So closed modularity locks users into a particular set of products or services, making it difficult to switch providers or choose alternatives without significant costs to users, without significant inconvenience, and essentially poses this existential risk to applications deployed on top and to organizations kind of dependent on those applications. Open modularity, on the other hand, embraces a much broader approach to modular design, where module production is permissionless and modules are interoperable across various core products or protocols. The key distinction being whether or not there is a privileged component or system that cannot be easily replaced by an alternate implementation. Open modular systems are largely based on principles of interoperability and decentralization. And in these systems, modules are designed to be compatible across different systems, networks, and every component should be replaceable, fostering this more inclusive and equitable developer environment and giving users greater choice of where they interact, of the trust assumptions they make, and ultimately more control over their property and their interactions with these systems. So while there's many benefits from open modular designs, I'd like to highlight 5 that I think are especially important in the context of Web3. So interoperability in an open modular system ensures that different modules can work seamlessly together, even if they're developed by different teams. This allows system designers to integrate the set of modules that work best for their needs, regardless of the team that developed them, fostering a technologically diverse environment. Using the basketball analogy, do the players have a common language and understanding of the team's strategies such that a new addition to the roster could easily be slotted in? When you're designing systems, you can ask yourself if your chosen component is using standardized inputs and providing standardized outputs so that it can easily be replaced with similar components also conforming to those same standards. Next up is permissionless innovation. So in an open modular system, engineers have the freedom to choose to create and distribute new modules and to compose modules into novel systems without seeking permission. This open design results in a really developer-friendly atmosphere and creates a space for healthy competition, which ultimately leads to better products and services as teams and individuals improve on their offerings and push boundaries for what's possible. Using the basketball analogy, imagine if only players trained by a specific school or coaches with a specific accreditation were allowed to coach. Actually, the latter is kind of true in a bunch of leagues, the former not so much. But when you're designing systems, you can ask whether you need someone's permission to build a component or to compose a system as a good kind of litmus test for whether it's, again, whether it's this kind of open modular system. The next piece that I think is really critical in Web3 is resiliency. So due to their tendency to spawn and support redundancy, diverse implementations of the same function, open modular systems tend to be more resilient with stronger security properties than their closed counterparts. This quality is particularly valuable for consensus-based systems. Multiple client implementations, along with a healthy balance of those clients being run by nodes, minimizes the potential damage that could be done by a bug in any specific implementation. Using the basketball analogy, what happens if a given player fouls out? Is there someone else who's available to immediately pick up the slack? Someone else that can be slotted into that role? And so when you're designing systems here, ask yourself, what happens if there's a critical bug in the implementation of this component? Can another implementation be slotted in to pick up the slack? Can it be kind of isolated from the rest of the system? All right, so portability and replaceability. Every component in an open modular system should be portable and replaceable. So forcing component implementations to compete on merit rather than on privilege status in the system. This reduces switching costs for users and limits their exposure to the fragility of any given implementation and the fragility of any given organization maintaining an implementation. Using, again, the basketball analogy, what happens if a given player does a season-ending injury, rolls an ankle, tears an ACL or something, and is out for the year? Do we have a viable replacement? Can we replace that player? When we're designing systems, we can ask ourselves, what happens if the company maintaining a given component in our system ceases operation? Can we viably replace that component with another implementation, and will it impose significant switching costs? What happens if the people maintaining a given component decide to deny us access to that component? Can we reasonably replace it or migrate from it without impacting the system? And finally, flexibility and adaptability. The previous benefits allow networks not only to evolve by integrating new modules, but often to maintain a certain level of liveness throughout that process. And because that same mechanism can support both diverse and evolving needs, a large range of users can be supported for a much longer period of time. This enables networks to continue to operate efficiently while still being able to respond swiftly and seamlessly to market conditions and cultural changes, offering dynamic components that are oftentimes missing in closed modular systems. Using the basketball analogy, we could think about a team, how a team responds when a new rule is implemented. The three-point lines move back, illegal defense is added in, refs start policing more strictly flops or something like this. Can the players handle that change? Does it require altering the rotation, altering the personnel on the team? Does it require a complete overhaul of the personnel? And when we're designing systems, we can ask ourselves, how would this system respond to an incremental improvement in some of the underlying technology? Could the new technology be easily incorporated into the system, or would it require essentially a rewrite of the entire system? In a modular, kind of open modular scenario, we can ideally replace just a given module, slot it back into the system, and maintain liveness, whereas more monolithic and more closed designs may require a significant overhaul of an entire system. In Web3, we see a bunch of these concepts play out in the networks and ecosystems that we engage in. The Ethereum ecosystem has made this really conscious shift towards ever greater modularity over the last close to a decade. A decade? Yeah. And we can see this clearly at the consensus and execution layers, where Ethereum is explicitly designed to support multiple client implementations across its network. So given sufficient client diversity, this design enhances Ethereum's resilience tremendously, as limiting the network's exposure to potential bugs in any of its various client implementations means that it's much less fragile. Ethereum is only becoming more modular, while all blockchains used to put their execution, settlement, data publication, consensus layers into one single component. Ethereum's moved in this direction of kind of separating consensus and execution into distinct components, and then making this larger step towards Rollup-centric scaling and a whole bunch of other applications coming online to modularize the other kind of critical components of building blockchain applications, things like data availability layers, all in a way that has not required permission from any given authority to enable, which is this really kind of critical marker for this open modular system. So with multiple implementations and separation of core components, Ethereum provides a nice framework for innovation and adaptation in modularity. In fact, we are currently witnessing this wild influx of rollups, app-specific chains, VMs, and other modular components as part of this wider expansion into modular blockchains. A whole host of projects, Eigenlayer, Celestia, Optimism, Arbitrum, Scroll, Succinct, Tycho, RISC-0, Hashi, Connext, are helping to increase the sophistication and diversity of Ethereum's modular components, allowing users and builders to construct systems from a wide variety of different components, tailoring and tuning the functionality, cost, and trust assumptions that make sense for their application and for their use case. Another example of modularity in the wild is much of the infrastructure that we've built at Nosa Guild. Zodiac is this really great example of an open modular standard for accounts. It provides a standard interface for composable and interoperable modular account tooling, where most previous programmable account implementations were built as this kind of monolithic and somewhat closed system. Zodiac decouples authentication and execution logic, enabling this flexible module-based control of programmable accounts, multiple control mechanisms in parallel, cross-chain accounts, and the ability for users to switch between tools and frameworks with really minimal friction. Our modules are most well known as part of the SAFE ecosystem, but we very deliberately designed it in such a way to be essentially agnostic to what the core account standard is. So as long as it conforms to this iAvatar interface, it can be applied to any programmable account. And so because of Zodiac's open design, many organizations have created their own Zodiac modules on top and started to develop this really phenomenal ecosystem of modules plugging into this kind of modular account core. This includes Connext, UMA, Kleros, Palmera, DAOhouse, and a whole bunch of others. So one last point I wanted to highlight here is the really critical role that standards play in this kind of open modularity space. Standards processes like the IETF's RFC process, Ethereum's ERC process, have this really critical role in enabling permissionless innovation. open standards allow for a diverse set of inputs and factoring in of many, many different real and potential use cases and applications that simply can't be considered when standards or implementations are designed in isolation. So open standards are this really critical component to enabling the kind of modular, open modular systems that I think are really valuable to the Web3 space. So just in closing here, as we look towards the future, we're clearly heading into an era of greater modularity, at least in the Ethereum ecosystem. And so I've been reflecting a lot on the Unix philosophy, that the strength of a system is not just in the robustness of its individual programs, but in their ability to combine with other programs, to build complex systems from simple modular components. We have an opportunity to embrace this philosophy in Web3 by creating tools that are not only efficient in isolation, but are fundamentally designed to operate in a variety of contexts and systems, enhancing the functionality and therefore the overall social and cultural impact that they can have. This approach encourages us to rethink how we build and integrate technology into our lives. Instead of adding an option or a feature in response to every need, we can consider where that need comes from and perhaps eliminate the need for an option in the first place by breaking our process down into modular components. In this way, components can act more like filters, transforming inputs into outputs that feed into the next phase of a process, allowing for efficient and adaptable systems. But perhaps most exciting is that open modularity lays the foundation for systems to evolve over time based on demands. Because of their permissionless and decentralized nature, modular worlds will become even more pluralistic and even more resilient as more engineers, builders, and users engage with them, engage and contribute to them. Just as ecosystems with greater biodiversity have a greater chance of flourishing, technical systems that adopt open modularity will be better equipped to handle future challenges. So as we continue to build and experiment with these novel technologies, open modularity should serve as this, not only as a design strategy, but as this guiding star that fosters diversity, adaptability, and sustainability. The broad, I guess, take-home message here is that when we're designing and choosing systems, there's a host of good reasons to prefer open modular systems, even if they sometimes require a little bit more upfront effort to implement or don't have quite as pretty of a user experience or shiny of a user interface. For the folks here participating in the hackathon tomorrow, I encourage you to think both about how the system you're designing could be built with existing modular components, and also to be wary of building atop systems that appear modular at the surface, but are ultimately closed modular systems, locking you into, kind of restricting your future design choices. That's it for the talk. Thanks for joining me to chat about some modularity matters. I'm Auryn Macmillan on Twitter, Auryn@nosasguild.org via email. I'll be around for the rest of the week, and then for the hackathon over the weekend. If you want to connect, come find me. Happy to chat.